So I want to welcome you to the final in our series of lectures for people who are interviewing for the GeV Stranathan Assistant Professor in Experimental Physics here. So we're pleased to have Viviana Cavaliere, who is now a postdoc at University of Illinois Urbana-Champaign. She got her PhD from Siena University in Italy, but at one point she got a Fermilab International postdoctoral fellowship to finish her PhD when she was for her PhD. But today she's going to talk to us about the Higgs boson and other stuff, so let's welcome Viviana.
Thank you very much. It is a pleasure being here and actually closing this series of colloquium. So today I'm going to be talking about the Higgs boson as a probe into the unknown, or as a second title, what is the life of our experimentalists after the discovery of the Higgs boson. So, well, I'll start from very far away on why we actually do particle physics, because I think it's an interesting question. Well, of course, we want to find an answer to the basic questions of mankind, particularly where do we come from, where are we going, and in particular, we're interested in understanding the fundamental structure and the laws in nature. So, from the larger dimensions in the universe, really to the smallest dimensions in the microcosm. So, this question has been asked for several times, so as I said, I'm going to start from very far away. We always asked ourselves, what is the matter made of? So our understanding before Christ, we just knew that there were 4 elements. Then, for instance, in the 1870s, Mendeleev came up with this periodic table that was putting in all the elements based on their properties. And then, as time passed, we discovered the new things, and in particular that the atoms are made of a nucleus. This is about the 1900s, and there is an electron the electrons that orbit around the atoms. And then going on, we discovered that the nucleus itself is not elementary, but is made of protons and neutrons. And then again, in 1960s, by keeping asking the same questions, what are we made of, we discovered that the protons themselves are not elementary particles, but they are made of what we call quarks. So today we have this understanding of the matter, so that is of the elementary particles that we are built of, that it's basically we are of quarks. There are 6 types of quarks, and of leptons. So you might be familiar with the electrons, but there are other leptons like the muons. There are millions of muons that are going through you in these seconds through cosmic rays. And then there are neutrinos, for instance. Same thing with forces of nature. So back in the 1600s, we knew that we discovered gravity. So we know that the Earth was orbiting around the sun. In the 1800s, we discovered the electromagnetic force, and that they actually come there. We knew that there was the electric force and the magnetic force, but actually Maxwell put them together and discovered that it was the same force. And then in the 1970s, we also discovered the force that held together the quarks within the proton and the neutron, that is called the strong force, and also the weak force. The weak force, that is the basically how the neutrinos interact, for instance. So for each of these forces, we have a force carrier of this force. These are called bosons, and you have them here. So you have the gluon, that is the carrier of the strong force. You have the photon, that you might be more familiar with, that is the carrier of the electromagnetic force. And then you have these 2 massive bosons that are the W and the Z's, that are the carrier of the weak force. So you might notice that here there is no carrier of for the gravity. That's because we haven't discovered it yet. So One thing you might notice is that the range and the strength of those forces are very different. So for instance, if we take the strong force and we set the strength to 1, you might see that the gravity is basically 10 to the minus 39. So it means that in the processes that we are seeing, gravity plays a very, basically a negligible, is negligible. And then of course, these are the strengths of the other forces, the weak and the electromagnetic. So we come here to the standard model of particle physics. So this is sort of a periodic table of our elementary particle and the force carriers. And we know that in 2012, there was an addition to it. There is the Higgs boson was discovered, LHC. This is just the seminar that was given at CERN, and there was even a Nobel Prize that was given to Englert and Peter Higgs for the discovery of this Higgs. That is the particle that it is believed to give the masses to all the other particles. So the question is that, is there all there is to know? So are we done with particle physics? So we know the Higgs boson? And the answer is really no. We still don't know if the Higgs is the only responsible for the mechanism that generates the masses of all the other particles, or for instance, why the masses of the elementary particles span such a 12 order of magnitude. So for instance, we have the top quark that is at about 175 GeV, and we go all the way down to the electron volt for the neutrino. So these we really don't know yet. So we think that there might be a more fundamental theory of which the standard model is a lower energy approximation. Then there are like other questions. So we know that there is dark matter out there from the motions of the rotational galaxies. We know that basically there must be something out there that is not the baryonic matter that we are made of and that we know so well. And then we also have this problem in particle physics that we call this hierarchy problem that I'm going to discuss a bit now in details, or naturalness. So what is this hierarchy problem that we usually talk about that involves the Higgs? So if you look at the calculation for the mass of the Higgs in the standard model, and you look at the one that we actually measure, that is 126, the observed is about mass of the Higgs is about 10 to the 32 times smaller than what it was predicted. So this means that there must be some cancellation that allows the mass of the Higgs to become so small. But let's think about how this can be possible. So if you have two numbers and you just of this range, so 0.7 and 0.4, you make a subtraction, you expect that this is of the order of 1. However, if you scale all these to 10 to the 32, you wouldn't expect this cancellation to be of the order of 1. So that's what we call basically the hierarchy problem. Sorry, I skipped one slide. So this is unnatural, that's what we say. So there is this problem with naturalness or fine-tuning that we don't observe in nature. So we think that there must be something beyond the standard model, and this is one of the reasons. So usually there are two grand ideas that try to pose solution to this hierarchy problem on naturalness. So one is the supersymmetry, who you might have heard about, and talk very little about this today. So basically there are new symmetries, and basically since there are these top patterns, then they allow the cancellations, and you get rid basically of this hierarchy problem. Or you just say that there is a new cutoff scale, so you don't have the Planck scale that is so different from the electroweak scale. And these are model composite Higgs model. So the Higgs itself is a composite object, or extra dimension if you want to go in more exotic models. And the idea is that now we really have a tool to look for all these models in sort of a model independent way, if you want. So you have here at the center the Higgs at 125 Higgs. So you can look at different things to look for physics beyond the standard model. So you just can treat it like top, W, and Z. So you can look for physics that decays to Higgs. You can look for other Higgses, so maybe like the Higgs is part of it's more complex, and so like there are more Higgses, and again these will decay in the Higgs. And then you can do also precision measurement, so you can characterize the state of the Higgs, so you can look at the properties and the couplings and make sure that they are standard model. And of course, like you can have exotic Higgs decay, in which, for instance, like the branching ratio can, of the Higgs into other particles can be different from what we expect. And today I'm going to focus really on this part. So I'm going to focus on a BSM particle that decays to the Higgs, or like searches for Higgs siblings. So for instance, like there are several supersymmetric models that predict new Higgses that then decay back to the Higgs. Or here you can have, or BSM, you can have extra dimension new particles that decay to the Higgs. So, I mean, as I said, really the Higgs is a tool for discovery because there are many extensions of the standard model that predict a new particle that decay to a pair of boson, and now bosons is also a Higgs. So you have the composite model, extra dimension, and here you can have pretty much anything that decays basically to one of these massive boson, W or Z or H. And the great thing is that you can look for this particle, so for these new resonances in a very easy way, because you can build the invariant mass of this system, and you expect the background to have like to be very smooth, while you expect your signal to be a peaking structure. So that's basically our moment of joy if we were to find such a thing. So where we do this, we do basically this at LHC. With proton-proton collision at 13 TeV of energy. So there are two multipurpose detectors, CMS and Atlas, and I'm working on Atlas, so that's what I will be describing. And the idea is that we use this to look for new particles and interaction. So you can really see the LHC machine as a time machine. That basically you can use it to examine the structure and the composition of the universe in the very early stage. And you can also look at it as a magnified glass that helps you see like what is really inside the smallest things of nature. So there are two important parameters in LHC. One is, of course, the energy, because more energy means that you can create more particles. And the other important things is the luminosity. So it's the number of effective interaction that we actually gather. And you can see here that basically how the relative luminosity, this is a plot from Atlas as a function of the Montina here, but for the different runs that we have had up until now. So we started very low in 2011, 2012, and then here we are now up here in 2016, where we gathered about 36.5 inverse femtoburn. So the Atlas detector, that's what I'm going to be describing. This is just one of the two detectors. As I said, the technology is a bit different from CMS, but what they do is the same physics. So basically, it's a camera with 100 million pixels. You can imagine it like, again, as a shutter speed of 40 million times per second that operates like for 24 hours for 7 days. And it also has a very sophisticated algorithm because we have basically only have one observed event in a trillion pp collision. So we want to be able to filter exactly the events that we want. So imagine that here we only want to keep the 0.001% of the events of our coolest peaks, let's say. We talked about the elementary particles, but now what do we see in the detector, really? So here we have something that we don't know what it is. So this decays. So what we see are the decay products. So there are leptons, that means like electrons and muons, for instance. Quarks, we don't see them free in nature. What they do is that they hadronize and they produce a collimated spray of particles that then we cluster together and we call them jets. So that's basically two quarks that would decay and they would produce two jets. Neutrinos, they don't interact, so what we use to infer the presence of neutrinos is that we use the imbalance of energy in the transverse plane. So how do we recognize these different particles in the Atlas detector? So this is a very simple transverse view. So we have different stages. Basically in the very center of our detector we have what we call trackers. So these are made to basically measure the tracks of the charged particles. Means that, for instance, like if we have a photon, this will leave no tracks in our central tracker. Then we have the calorimeters. The calorimeters basically are here, they are over here. They are made to measure the energy of particles, and the only way that you can measure the energy of a particle is that you need to have them lose all the energy in the calorimeter in order to be able to measure it. And then we have other the muons. They don't interact with they don't lose all their energy in the calorimeter. So we have to build some other trackers for specifically for muons. So based on this, we can already tell which particle we are looking at. So for instance, if we have like a charged particle that also has a deposit in the electromagnetic calorimeter, then we will know it's an electron. If we have a deposit in the electromagnetic calorimeter and no tracks in the tracker, then we would know it's a photon, and so on. So the jet, that's how we would appear in the calorimeter, and a muon really it's one of those particles that will survive the calorimeter, and so you will see some hits also over there. And as I said, the neutrino we don't see, it doesn't interact, so what happens is that we just use the imbalance of the energy. So we start from the detector, then basically we have some sort of trigger. So this is the filtering that I was telling you about. That is very important because it allows us to store only the events that we are really interested in. We have the reconstruction, we do our analysis, like we have our backgrounds and hopefully some signals, and we go to the publication. And I just wanted to stress a bit like the importance of trigger, because really like if we are able to resolve the complex topologies that we are looking at is really thanks to that. Okay, so today, as I said, we are going to talk a bit about resonances that decays to VH, where V stands for either a W or a Z, so it's a massive weak boson. And in particular, we are going to be talking about the WH channel. So like you have a W that decays to a lepton neutrino, where the lepton, as you can see, is one of those. And the Higgs decays to BB bar. So okay, the arrow is, for some reason you cannot see, but this is basically the Higgs branching ratio as a function of the mass of the Higgs. So we know that the Higgs is about 126. So you can see that basically about 58% of the time it decays into BB bar. And as I told you, we cannot see quarks free. So what we measure, what we actually detect are jets. So let's talk about now a bit about reconstructing these boson decays. So you have these particles that decays to WH. So at low mass, the boson, in this case the Higgs, has relatively low momentum in the lab frame, so we are able to reconstruct one jet for each quark. While if you go to very high masses, so for masses like greater than 1 TeV, then the boson has a high momentum in the lab frame, so that means that the outgoing quarks are very close together and the jets begin to merge. So the idea is that if you want to look at very high mass resonances, in this case, you cannot just use two jets, but you use a large radio jet to pick up all the radiation from this decay. So how do we distinguish the signal? The signal in this case is a jet that comes from a boson from a jet that will come from QCD. So in the boson jet, you have two narrow regions with high energy for each quark, where each of the quark carries comparable fraction of the boson momentum in the lab frame. While in the case of QCD jet, you only have one narrow region with a high energy density that has most of the momentum of the jet. In one case, the jet mass, so if you go and look at the mass of the jet, that originates from the boson, so it's exactly at 91 if we look at the Z, or 125 if you look at the Higgs, while in the case of a QCD jet, the jet mass originates from the spread of the energy deposition by the single parton in the final state radiation. So it's essentially random. So basically, one thing that I want you to remember is that when you go to very high masses, one thing that will happen that these two narrow regions from the boson decay will start to overlap. So this means that basically new algorithms are needed. So how we developed both in Atlas and also in CMS like this whole concept for boosted boson tagging, and basically what we do, as I said, is that we reconstruct this larger jet, so to pick up all the radiation from the original decays. Then we apply what we call grooming. There are different techniques available, but what this actually does is that for the signals, it takes out the constituent that don't belong to the jet, to the signal decay, while for the background they just preserve the characteristics of the jet. And then you do some tagging. Again, this is jargon, but basically what this means is that we use the differences in the signal and the background, the jet characteristic, to reject the background. So for instance, here I have a plot of the jet mass. This is one of the observable that is usually used, as you can guess. So here is like in the case like it's a signal jet, and here like in the case of QCD jet. So you can see that is a variable on which we can cut that is really a distinguishing signature between signal and background. In the case of the Higgs to BB, you have also one other thing. So you know that the Higgs decays to for 58% of the time to BB, and you know that the B hadron basically with a mass of 5 GeV has a very long lifetime. So basically, if you have a B hadron with a PT of 30 GeV, you can calculate the decay length, and you can see that basically you have measurable displaced vertices. So this thing basically travels for about 3 millimeters. So, and then you can also have, you know that most B hadrons decay to C hadrons, so in some cases you can also find that another vertex in the B hadron decay chain. You have also other information, so you know that 40% of the B hadron decays are semi-leptonic, so you can have 10% for a B that goes to lepton directly, and then you can go through the C where there is an additional 10%. So you can also use all this information to actually design B taggers that will help you also discriminate between the signal and the background. So most of the algorithms are lifetime based. That means that basically what they do is that they measure the impact parameter, and that basically means exploiting the compatibility of the track with the primary vertex or the incompatibility. You have like inclusive secondary vertex algorithm. You also have lepton ID based. That means like you use basically the leptons inside the B jets, although they are not quite used in Atlas any longer. And you can also have multivariate techniques that basically take all this information and build it up in a tagger. And the nice thing is that this can be applied both to the jets, to the smaller jet, so in the case in which the resonance is a low mass, or in case it's a large mass. Because in the case of the larger jet, you can apply the B tagging to the smaller jet that you can reconstruct inside, made of tracks. So that's what we do in Atlas. So basically, we reconstruct the track jets, so the liquid tracks are measured with the tracker, and we apply B tagging to these small track jets. So going back to the analysis, again, as I said, we want to measure like this, we want to look for this particle that decays to WH. So the W is reconstructed, we require one isolated lepton, electron or muons, and we use the imbalance in the transverse plane to measure the missing ET. And on the hadronic side, sorry, here I should say Higgs, you ask for one larger jet with one or two tagged track jets. And here is a plot basically of the jet mass. So it's very hard to see, but if you look at the signal, that in this case it's a particular, it's a resonance that decays to WH. So in this case the H should be here, so it's around 125. So what we do is that we cut around in a window from this variable, that is the jet mass, and this will be like our signal region. And this is also very interesting because you can use the sideband to actually get an handle on the backgrounds, on the normalization, because all these are basically extracted from simulation. So what are the backgrounds, the dominant backgrounds in this analysis? So you have W plus jet, so B jet and C jet production. So you have exactly the same signature in the detector of the signal, but which much higher cross section. And we have simulation that tell us how that should look like, and basically we use that in our analysis. Another very important background is TD bar production. In particular, here you have the TD bar that goes to WB, where one of the W goes to leptons and the other W goes to jets. And so here you reconstruct the larger jet. But here you have a handle, because here you are expecting two more B jets in the event. So if you ask for no additional B jet in event, you can substantially reduce it. And then you have also like these what we call QCD multi-jet events, that are events with semi-leptonic hadronic decays or misidentified jets. And what we do is that we use poorly identified electrons or muons to model this jet that fake our leptons. And basically then we use the missing ET distribution as a discriminant, because we expect this fake jet to have very, very low missing ET and our signal to have a large missing ET. And all these backgrounds this is data driven, but the other two are extracted from simulation, from what we call like Monte Carlo, and we check them in control region. So if we go back here a little, so we have a very nice way of defining our control region that is close enough to the kinematics of the things that we want to look at, and we can use basically the sidebands and look at other distribution to make sure that they agree very well between data and what we expect. And then we can go ahead and, well, I'm going very fast here, but this whole procedure takes a long time to go and look at this plot that are the final discriminant that we use. So here is basically the total invariant mass of the system. So it's the MV plus the Higgs, so the WH system. And here, for instance, is in the case of 1B tag, and here is the case of 2B tag. And you can see here how a signal will look like. Actually, here have been scaled by 50 just to see like how we will the shape of the signal, but we don't expect it to be so big. And you see that basically the data is very in good agreement with the background. So unfortunately, we don't observe any standard model, any excess over the standard model background. So what we provide are these rather disappointing from a point of view, because that means that we have not seen any new physics, but we have these limits on the cross-section of the production of these resonances that decays to WH as a function of these new resonances. And basically here you can see these are the upper limit on the cross-section that we might observe. And if you take the theory line of any any theoretical model that would predict such a resonances, and you put it here, if they have the same kinematics, then where they cross, they will tell you like which masses are basically excluded. So here we can tell that in this particular model that we are using, that is just an effective field theory model, is basically we are excluding masses below 1.7 TeV. That doesn't mean that like we won't see in the future anything below 1.7 TeV. We just means that if you have something with that cross section predicted, then you would be able to exclude it with such an analysis. So these plots, as you can see, are with a bit less data. In particular, these are the first data set that was collected with 2015, so it's only about 3.2 inverse femtobarn. We are in the process of analyzing the rest of the data, that is about 36.5 inverse femtobarn, and the idea is that the results will be out by the Moriond. There is this big conference that is coming up in March, hopefully. And we also have the data of run 3, where we expect about 300 inverse femtobarn, so these are pretty exciting times. And here are just some, for some of the models, so this in particular is an extra dimension model that decays to VV, and this is just a W prime that would decay to VV. What are the mass limit that we would expect to put? So we are right here now, so in 2016, where we expect to be able to probe resonances up to 1 TeV for this particular model and 2.1. And you can see that basically already when you go to 2022, that is basically the end of run 3, we will be able to probe very, very high mass resonances, in particular go all the way up to 4 TeV. And just as a scale, here I put the number of events for the other standard model processes that we expect in the future to come. So is looking for resonances the only way to actually look at, to search for a new phenomena beyond the standard model? So the answer is of course no. So it's really the most dramatic signal for new phenomena, but maybe like this new physics might be too heavy or broad to be clearly seen at the LHC. So there are other ways to look at new phenomena, but like you need more luminosity. So for instance, you can find here, this is just, doesn't have any particular meaning, but you can look at other distributions. So for instance, that PT distribution, differential distribution, where you expect, for instance, like a certain shape for the standard model, your standard model background, and you can look at some enhancement when you look at the BSM phenomena. But in order really to be able to distinguish between the two, you need a lot of more luminosity than just what we have. So the idea is that we will have this run 2 with 13 TeV, and then we have the run 3 we will increase the energy to 14 TeV, so it will be another step in energy and also a step in integrated luminosity because we expect 300 inverse femtobarn. And then the LHC will be upgraded to what we call the high luminosity LHC that will bring about 5 to 7 times more luminosity basically at the same energy. And you see here the scale, we are talking about 2026, so about 10 years from now. So at the high luminosity LHC, there are several things that you can do, and the Higgs is always at the center. So this is just an example that I wanted to show you, is that you can do like also the other ways of looking at new physics using the Higgs. So you can have like, again, resonant production of the Higgs, but you can look at the standard model Higgs production, that is a direct test of the Higgs potential, but has a very small cross-section at 14 TeV. That's why you need more luminosity. And if you have beyond the standard model physics, that means like if you have additional Higgses, then you can have also like this modified coupling, lambda, where basically is the Higgs self-couplings. And the way that you look at it is that you can do these non-resonance searches, and you can look at the deviation in kinematic distribution and the cross-section predicted. So you can look, for instance, for deviation from the expected shape in the mass of the Higgs, but also the PT of the dye Higgs. And you can see that basically what you would expect in the case of the standard model and what you would expect in some other cases in which basically this coupling is different from the standard model. So here you really have a lot of final state that you can explore, right? Because we looked before at the branching ratio of the Higgs. The branching ratio goes mainly to bees, but it goes also to, can go to 2 taus, to diphoton. And here is basically the list of the dye-Higgs branching ratio. So you have the biggest one is for the 4B, that is about 38%. But you also have here some other ones, the 2B, 2Ws, and 2B, 2 taus that are very high. And the ones that are highlighted are the ones that we have analysis also going on right now in Atlas. So some of these are very hard because they are dominated by the background. So for instance, if you look at the 4B final state, this is a very challenging final state because you have 4 jets basically. So imagine your QCD cross section is like very high. Same thing for the 2B, 2W, basically you are dominated by TT bar. This is exactly the same final state. At that point you don't have any handle on your background because you still have 2 other B's in your final state. You have the 2B, 2 taus. Again, these are very hard. And one thing that I wanted to point out is that while now we are looking at resonances with very high mass, so we are not worried about how we trigger on those events because the threshold, the PT threshold on the object that we reconstruct at trigger level are very, can be as high as we want. When we go and look at these non-resonant decays, that means that we want to look really at the differences in shape here. This is actually the PT distribution at low PT. So that means that it's critical that we keep triggering on this object with a very low threshold. So I just wanted to leave you like with this slide that is not very related to the analysis, but to make you understand that really the challenge for dye Higgs, but not only for all the analysis that we are going to do at high luminosity LHC, is basically that after the shutdown, we are going to expect about 200 simultaneous proton-proton collision, and this is actually a plot from CMS that shows 80 simultaneous PP collisions, so imagine 200. And the biggest challenge, especially to reconstruct those important decays that are 4Bs and 2B, 2 taus, that are the ones with the highest branching ratio, is going to be the trigger. So here, the important thing to reconstruct those objects that are B jets and taus is really the signature that they leave in the tracking system. So you need tracking already at trigger level to control the rates while maintaining good efficiency for the relevant physics processes, but also like to determine the position of the primary vertex. Why you want to do that? You want to know what is the primary vertex inside all those 200 simultaneous collision to get rid of your pileup. So at high luminosity LHC, you really will have many tracks of charged particle that you will have to find in a very short time. So that's about 60 million per second. And that means that you cannot do it any longer with software. So you cannot do just track finding via software, but you need something hardware to be able to do it. So if we really want to keep doing physics, not only with the Higgs boson, but good physics at high luminosity LHC, we really have to start thinking about this. So actually this brings me to my conclusion. It was very fast. So we talked a bit about how naturalness and dark matter point to new physics in the reach of LHC. So all the models actually predict some new physics at the TV scale. That is what we are looking at. And so we really need higher energy and more luminosity. So we have these grand ideas that solve the puzzles of the universe, of the hierarchy problem, that are our guides in designing our searches. But what we know is really the Higgs is at the center of it, and we should keep using it as a tool for look for beyond the standard model phenomena. So our goal is to discover new physics if it is in our data, and this is obviously not a trivial task. So that's why we need to cast as wide as net as possible in the hope of finding it. And to be able to keep doing such physics in the future, we need to be ready to keep collecting the data. So I just wanted to leave you like with these upgrades, and in particular start thinking about the future and how we're going to trigger in the future is really necessary. Okay, thank you.
Questions?
It was very clear. Yeah.
On the limits on the W prime,
Yeah.
what production mechanisms were included in those efficiencies?
So if the efficiency are included here,
What production mechanisms for W prime were used? So
in this case, these are for specifically for just the PP that decay to W prime. So it's just they're just the standard production mechanism
So
for the
just
W prime.
just draw around?
Just QQ, yes. Yeah, there was another thing. What we are looking at is a different, now we are just starting looking at it, and maybe for the summer we'll get a result, another production mechanism, and in particular we are very interested now at vector boson fusion, so where you have two additional forward jets that you can use to tag on, but up until now we have not started looking at this yet.
How far forward in NATA does your tracking go?
Well, the good tracking. No, so for tracking, we, for instance, like B jets and other stuff, we already construct up to 2.5, but then we have, but we jets usually we extract up to 4.5. So.
Okay. Are they posted?
Yeah.
On your Higgs, double Higgs production,
Yeah.
which shows different decays, you mentioned that the 2B, 2W has a TT bar background.
Yeah.
Are the thresholds very different? Good handle.
Well, that's if you're talking about resonant production. Yeah, so like, in that case, yes, that will be true. But if you're looking just at the non-resonance, then I think, the threshold will be very similar. Anyway, actually, I should put this in sort of like bluish, because there are studies that are being done with 2B, 2Ws now in Atlas, not only actually, also in CMS, and there are several studies for high luminosity LHC to be done, 2B, 2Ws.
Other questions? Okay, well, let's thank our speaker again.